My name is Miko Yang.
I'm Jack Wu.
We are from Caxton College. Our supervisor is Miss Julia Rocher, and our project's name is called Superposition of Magnetic Fields.
When we learned that Maxwell's equations describe electromagnetism in such an elegant and unified way, we were excited to explore them further. So, we decided to take one of their core ideas, that an electric current generates a magnetic field, and design an experiment around it.
This is a sketch of our experimental setup. The red and green lines represent two separate current loops. They are arranged in layers, so one on top of another. The direction of the current in each loop can be individually controlled just by switching the polarity of those batteries. By observing how strongly the iron rod attracts iron filings, we can visually compare the strength of magnetic field under different current directions and configurations. This is a failure because there's no iron core inside, so it has limited attraction even to the permanent magnets. This is the experiment setup. We use a mobile phone to shoot close up and project the screen to an iPad. Although the experiment is a little bit crude, it very cleverly demonstrates the electromagnetic principles behind it. Now, let's take a look at the experiment results. First, we tested whether the two circuits could be powered separately without interfering with each other. The result matched our expectations. Both loop A and B successfully generated the iron magnetic fields and showed very similar attraction patterns with iron filings. This confirms that the current in each loop can be controlled independently and that the magnetic field strength is nearly identical in both.
Then we powered both loops at the same time, with the current flowing in the same direction. We first turned on loop A, and then added loop B a moment later. As soon as the second loop was powered, the iron filings were instantly put in with much greater force. This result confirms that when both loops are aligned and the current flows in the same direction, the resulting magnetic field is stronger than that of either loop alone.
Now, let's look at the effect of destructive superposition, which is the climax of our experiment.
On the basis of powering loop A, we reversed the direction of the current in loop B. The iron powder desorbed instantly. This means that the magnetic field was cancelled. To find the direction of the magnetic field created by the current in our coil, we can use the right-hand rule. Imagine gripping the coil with your right hand, so that your finger curls in the direction of the current through the wire. Then your thumb points in the direction of the magnetic field inside the coil. That's from the south to the north end of the electromagnet. This tells us that the electromagnetic field lines run through the center of the coil, along with the iron core, and came out from one end, just like a bar magnet. Using this, we can predict where the iron filings were gathered. They will be most concentrated at the magnetic poles, which are the end of the iron core.
This experiment successfully visualized the induced magnetic fields by using the iron filling. Our conclusion is that magnetic fields add up like vectors. They can reinforce or cancel out each other depending on the direction of the current. This explains why when current flowing in opposite directions, the magnetic field partially cancel each other out, resulting in almost no net effect on iron filling. In addition, this video demonstrates the role of the iron core inside the coil. It helps concentrate and guide the magnetic field lines, significantly increasing the magnetic field strength.